Welcome to this part of the video lessons of class 12 physics. In this lesson we will learn about the energy stored in the capacitor. We have learned about the capacitor, that we can give charge to this, and this way we can store energy with the capacitor. And how much energy can be stored, what is the mathematical expression, this we will see here. And also we will see other terms like the energy density of parallel plate capacitor, and when the capacitors are joined, then what happens to the energy of the system. So we will see the energy loss, and this energy loss due to what? Due to sharing of charges. So let us begin with the energy stored in a capacitor. What is the energy? We have learned that work done in giving charge to the capacitor is stored as the energy. Now the question is, why the work is done by the external agency when we are giving the charge? You can understand that if this charge is given in small steps, then next increment of the charge, if we want to give to this conductor, then it will not be easy, because we will experience the force of repulsion. So it is not easy to go on charging anybody. Continuously we will have to do the work. External agency, that's the battery, has to do the work. So here is the capacitor, plus charge and negative charge, and uniform electric field from plus to minus. Let the A be the area of the capacitor and V the potential difference between the two plates of the capacitor. Right? So here it is the charge capital Q which we have to give to this capacitor, and let at any intermediate stage, that is at instant t, the charge possessed by the plates be small q, so that its potential is V dash, not V. V is the potential when there is a charge capital Q. Okay. So when the charge onto this is a small q, let the potential be V dash. Now further, if we want to give the charge in increment of dq, then the small work done, infinitely small work done to give additional charge dq to the plates of capacitor will definitely be V dash q, V dash dq, or V dash we can write hence q upon c into dq. And to give the total charge capital Q, we will have to integrate this work done. So total work done in giving charge capital Q, we will have this. Integrating, we will have Q square upon 2C, or Q is equal to C into V we can write. We will have also for the energy 1 by 2 CV square. We should note in our mind that energy of the capacitor lies in dielectric medium between the plates and not on the surface of plates. So whatever medium is there, air or the dielectric, right, the energy is there. And also that the total energy is stored for both series or parallel combination of capacitors is the sum of the energies in the individual capacitors. Right? Now let us see the energy density of parallel plate capacitor. Energy density simply means the total energy per unit volume, that is volume of the dielectric medium between the plates. So A is the area, D is the distance, then volume is going to be how much? A into D. Total energy is 1 by 2 CV square. Right? So we will have this energy density, which we will denote by small u as 1 by 2 epsilon naught E square. We can put these values for the capacitance and V. We will have the energy density 1 by 2 epsilon naught E square. Now let us discuss about the sharing of charges when the charged conductors or two charged capacitors are connected. So we want to know the common potential. Whenever charged conductors or the capacitors are joined, what happens? The charges are shared till the common potential is reached, right? And charges are shared and the energy is lost, right? So to what amount these all things will happen, let us see. On joining two charges, on joining the two charged capacitors, the charges are shared, right? So that the potential becomes the same of the two capacitors. However, the total charge before sharing, we will have Q1 plus Q2, Q1 plus Q2. So we will have C1 V1 plus C2 V2. And after sharing, we will have Q dash. Again the total charge of the system, Q1 dash plus Q2 dash. Potential now becomes the same. So Q1 dash is C1V and plus Q2 dash C2V. But charge conservation tells in both the cases these charges should be the same. So let us equate them. We will have this. And for common potential we will have this term. That is C1 V1 plus C2 V2 upon C1 plus C2. And of course, sharing of charges. So we will have Q1 dash let us learn one more term, that is we will have Q1 dash is equal to C1 is the charge after joining, and what about the potential? C1 into V. Potential becomes common now. And on the second one, charge how much? Q2 dash. This will be equal to C2 into V. Alright. So Q1 will be C1 V1, Q2 will be C2 V2 before joining the capacitors. After joining, we will have Q1 dash as equal to C1V and Q dash to C2V, and that Q1 dash upon Q2 dash is going to be equal to in the ratio of their capacitance. So Q1 dash upon Q2 dash will be equal to C1 upon C2. Common potential we will have. Now let us learn about the energy. So total energy before sharing, we will have this. After sharing of charges, total energy after sharing charges, that is after joining the capacitors, right? We will have this 1 by 2 C1 V square because potential becomes common, same. Alright. We can use the equation for the common potential here and calculate U1 minus U2. That is the difference of energy of the system before and after the joining of the capacitors. Solving the terms, we will have this. Simple mathematics. After putting the value of V here, then subtracting U2 from U1, we will get this. This term is positive because the square of any difference is the positive. The difference is whether negative or positive. Square is going to be positive. This positive means which is greater? U1 or U2? U1 is greater. Right? So what does it show? That energy on sharing charges is lost. energy loss is there. And this loss may appear in the form of the sparking, or the connecting wire may get heated up.